Hello everybody, and today we'll be talking a little bit about shadow and penumbra and umbra. What are this and how we can measure it, quantify a little bit and see what can be done. So I made a picture, a photo of using my camera. You can see the parameters on the left. And the picture here is of a wall in my room. And on the wall is white, but it has a little bit of this pattern, like flakes. I put a measuring tape vertically. It's in centimeters on the left and inches on the right. It's vertical and glued to the wall. And my room is illuminated here by basically only one source, primarily only one source. It's a small torchlight on the other side of the room, at a slight angle to the wall. It's just because I don't have exactly two opposing walls easily accessible. There's always something hanging or something like that. And between this light source, this torch, which is the torch light is maybe 12 millimeters in diameter, and it is small torch, has a very pretty narrow beam of light, a cone. It's not shining in every possible direction. It has a definite edge, so you can point it better when you're looking for something in the dark. That's why the edges are pretty dark here, but the center is relatively okay. And between the wall and the light source is my finger. That's my finger, shadow of my finger that you can imagine it would form. And this is my camera, shadow of my camera and tripod. So my finger, this is an index finger of my left hand, the second after the biggest one. I don't know the names of my fingers. Thumb, and then there'll be the pointing one, the one you use for pointing, the second one. And it's pretty normal. It's this we see here a side view. I was putting it on a side. So I would say it's about 9 millimeters. My real finger is about 9 millimeters thick, maybe 1 centimeter, 10 millimeters. And it's substantially bigger here because of how light and shadow works. And it has this really well defined black region, dark region, and you can kind of see this other region, which has transition between dark and white, the dark and bright. But also this region ends, and you can kind of see it. It ends about here. This. So we call this area of full shadow and umbra, and this transition period between umbra and the background, penumbra. So let's load this image into some image editing software. We'll open the raw file because this will allow us to get a bit more dynamic range, which will reduce the noise, especially in the dark areas. So we'll just close it. It will start opening, and I'll pause because it can take a bit of time. I'll be back in a second. Okay, we're back. It's still loading, but I hope. Oh, yep, it's opened. So the GIMP cannot open the raw files directly, so it asks the other program to convert it to something that the GIMP can open, and this conversion takes time, and then it needs to be loaded. So we have this image now, the same size, but now it's in a higher dynamic range. And if you look at image mode, it's RGB, precision is 32-bit floating point, and linear. So the value of each pixel, numerical value of each pixel, is actually proportional to the light intensity as measured by the sensor, which if you just load the JPEG file or some other 8-bit files, it will be usually in sRGB, which is where the value of the pixel is not proportional to the intensity of the light. It's using something called gamma correction, and sRGB is a variant of gamma correction. We want linear light to do any reasonable manipulations of light and values of light and plots of values of this intensity. So we'll be working in linear light. We'll actually convert it to grayscale. This will help us a little bit because this will average a little bit of noise will be averaged, and will also be easier to plot. It's easier to plot one value. This conversion back to gray leaves the same parameters here, and it's using the uh, standard coefficients of R and G and B to convert to gray based on a human perceptual model. You can check this out on Wikipedia easily, like RGB to gray conversion, and in GIMP manual probably too. So we'll focus on a part of the picture that is mostly similar in RAWs. So we'll grab a piece of the image that is relatively, that each horizontal line is roughly similar values. Let's say here, right? If I would draw a line, each line has a very similar intensity. So we'll grab this, copy it to clipboard, copy, paste as a new image, and now we have only this one strip. It's the same height as before, but just this one strip. Right? This is a part of my finger, and yeah, each one is a little bit yeah, it's uniform in this way. We are going to do resizing, I think, using this is the best way. The precision and mode and everything is the same. So scale, and we'll unlock the aspect ratio. This is aspect ratio. If I set 1 here, it will change to something here. We don't want that. So we will go here and slowly reduce the size in width, effectively averaging the pixels. And I don't go directly to 1 because GIMP is not smart how it is doing. So I'll go to 100, 50, reset, 50, scale, 25, scale image, let's say 10, 16, let's say. Four, nope, 4, 2, 1. And the reason I'm going for 1 pixel is because then we can plot plot this data easy using some programs. And now this pixel is basically an average of all the original pixels in this strip we selected. And if we go to about where the middle of the shadow is, which is about here, we can see the coordinates are 1996. So let's go to the same value here. 1996. Yep, it's dark, right? Just as we expect. This is supposed to be dark. So now we'll save it. Export as a strip gray. Before we do that, we need to reduce the dynamic range a little bit to 16-bit. This will not change much. As you can see here, it's still black, and here it's still bright at the top and bottom. The reason is, I want data that is readable by a program that I'll be using. So now export strip gray, export as ASCII, and now we should have this file, strip gray. It's a text file, so we can look at it. It tells us this is a gray, one color format, one channel, only gray. This is a width of 1 pixel, yep. This is height. This is the maximal value of the pixel. This is a maximal value of 16-bit signed integer. And then there's this first pixel in the first row, the second pixel in the second row, and so on. And it goes and goes up, and goes down. There's this dip, dip, and so on, for 3000 something pixels. So now we'll use a plotting program to remove the first 4 rows and only focus on the pixels. This is to plot a pixel by the pixel position from the top. Really nice. Oh, that's beautiful. It's actually better than I tried before. It has very little noise. I'll also put the grid. So what we are looking at here is the axis on the bottom is pixel position. So this is the height 0, and this is height 3000 something, 3800. Yep. So the pixels on the left here, on this graph, this points, are the pixels on the top of the image, and pixels on the right of this graph are the pixels on the bottom of the image, of this strip we cut. And the left axis is the intensity between 0 and 65,000. We don't go to 65,000 because the entire image wasn't actually super bright. And this also means there's no clipping, there's no flat parts, they don't reach to full brightness, they don't reach to 65,000. So we see the full scale of image. And the first thing is this bright region here and here on the outskirts. This is a background, this is the brightness of the wall. And if there will be no finger in the between the light source and the wall, this will continue a little bit up, and then go down. This will be a little kind of like, I don't know, some kind of parabola, maybe a circle. It's really hard to say, but it goes up and down. So the center of the torch was shining somewhere here. And as I said before, it's not omnidirectional source, and the angle of the light wasn't exactly perpendicular to the wall. And there's also a bit of vignetting from my camera, maybe, but very little, I think. So basically, because of this, the light is the cone is limited and it's beamformed to shine mostly in one spot, a spot line or beam. This is why most of the light is in the center and then goes down on edges. The reason this part is a little bit higher than this one is because this is a top side, and top side is closer to the ceiling, and the ceiling receives some light from the torch and bounces it back, and it bounces more to this area than this area because it's a bit closer, so it's less diffused, less scattered. At least that's my theory. The difference is pretty small. Then we have a shadow. This is the shadow from here to here, and this is the main part of the shadow, the darkest shadow, which we call umbra. The reason it is not zero there are two reasons why the level of this umbra is not zero. The one reason is there's always some bouncing light in a room. The rest of the room is not perfectly blacked, or it's not big room. So once the torch, light from the torch hits a wall, even the wall we are looking at, it reflects back into all different directions, not just us. It also goes to ceiling, as I said, and it also goes to side walls and back walls, and from there it bounces back again. And you can easily imagine that it bounces to the left wall at some point, and from that other wall it bounces back to the wall we are looking at. And from this other angle, from this other wall, it will not be occluded by the finger. Finger is way back. So even this area of shadow will receive some light from some other bounces from other angles. That's a primary reason why it's not complete dark. And a second reason, of course, is also the sensor is not perfect. There will be always some noise, there will be always some bias, probably very little, but that is it. So this is this area of full shadow. We will ignore this background. Sometimes we call it ambient light. That is average of light coming from all directions, not just from strong source points. And beyond this full shadow, umbra is a region of slightly slowly increasing brightness as we go far away from umbra, from that. It's called penumbra, and we can see it on both sides here. Goes pretty linearly, falls back a little bit, goes a bit slower later, then reaches background color, background lightness, and disappears. It's no longer there. So umbra stops here, penumbra, sorry, stops here, and then we have background color, background brightness, and the same from here. So let's do measurements and plot them on a chart. I zoomed in a little bit, and we'll say that umbra is from 1874. So let's do that. I will put a guide 18. What did they say? 18. kind of a little bit subjective. I'd say 1880 plus minus few pixels, 1880. 1880, yep, here. And on the other side, on the bottom, probably here. That's 2100. 2100. 2099. Yes. And let's do the same with the Penumbra. So we'll zoom a little bit here and we'll say here. Maybe here. Yeah, let's do this. 1325. 1325. 1325. I'm looking at this value here in the corner. 1325. And on this side, maybe here. Probably here. I'm not sure if averaging worked because there's like a little bit of modulation here. It looks like a pattern of my wall. Let's say here. That's 2600, 2653, 26, 2653, 53 here. I need to zoom a bit more. 53. Okay. So this defines Umbra region and Penumbra region. So we'll add a new layer, legend, and we'll put a bit of text here. Umbra. What happened here? Why it's gray? Is this image gray? Ah, yes, of course it is. Layer. Can I have a layer with different mode? I don't know. Let's keep it gray. That's Umbra. This region between the two, and then we have a Penumbra. And also here, Penumbra. Penumbra. Like this. And to not make things too confusing, we'll cut and make it smaller. So I'm referring to these regions here. Penumbra, Umbra, Penumbra here. We're mostly focusing on this region here. And there's a trick we can do also to find these regions. We'll duplicate the layer and rename it to Umbra and do color manipulation using levels. And to show that I'm not biased, I will actually hide this guides. So now we can do transformation of color using curves. This also can be done using levels, but I like this method. And we'll bring out all the shadow to be very bright on this layer. And improve a little bit of contrast here. I think that's good enough. Okay, so now we have our Umbra. I'm only showing the most dark parts of the image. And the reason there are some white dots is because they're slightly brighter than complete darkness and there's a bit of noise. But this allows us to see Penumbra. This is my finger. Yeah, this is a pointy end. And on the legend, we'll put a bit of an outline here. Okay, and the same here. Yeah. This line is because it's trying to snap to guide. Even if it's not visible, it's trying to guide to the snap. So that's here. Okay, so now we can hide our image with stretched colors, and this is area of complete shadow, the Umbra. Now we can do a very similar thing with Penumbra. We'll do a duplicate layer, Penumbra, and do color manipulation using curves. And now we'll only show the very bright picture, very bright colors. Not if there's any hint of shadow, we'll make it black. And I would like to make it on both sides like this. And you can clearly see there's a little bit of light here, a little bit of light. This is the background. And again, the reason that there's a darkness on the outside is because of this fall off at the end, right? We are trying to only show this part, the very peaks, and and because of that, everything that is outside of these peaks will be dark. And yeah, so this is why the outside is also dark. With better setup, with more uniform light and so on, maybe it could be improved, but there's still always probably be some fall off. So with that, we can see, we'll put a legend here, and now there's a bit of a question, where should we put the line? Is it here or is it here? I would say it should be here, because we still see gradient, right? There's no gradient here. Actually, from here, come on, why I cannot undo? Trying to do undo. There's no gradient here. It actually goes back. So what we're really looking at is, where is this transition region? Why cannot undo? Oh yes, I can. On legend here. So it's somewhere between here and maybe here, somewhere here. And very similar thing can be done here. It's a little bit darker, but I'll semi-subjectively put it here. Okay, now we can hide it and show back our picture. And now we can actually bring back our guides and see how these things match. Remember, we were only focusing on a small strip about here. So view guides. Ta-da! As you can see in this strip, you can see that there's some transition, and this transition region ends here. And one method was using a plot, this plot. Another one was using changing the levels and curves. And some people can probably just do it by hand by looking at it. And here, Umbra and Penumbra. Yeah, there might be a bit of variation, I guess, there, here and there, but let's see. The more conservative version is the guide ones. It shows us here there is there's 51 and 47. So that's how much that is? No, 407. 407. So that's, is it? That's 56 millimeters. 56 millimeters. 56 millimeters. Let's make it brighter, maybe. Yeah, 56 millimeters. This is Penumbra here. This is Penumbra, and this is Penumbra. Yeah, 56 millimeters of the full Umbra shadow. My finger is not 56 millimeters, definitely. We can also make the same measurements here just by counting pixels and finding the scale factor. And we can actually do this here. We'll just measure from 10 millimeters online and we'll measure up to 80 as far as we can, because the further you go you get better smaller relative error. So this is 2697, 2697, 2697, and this was 700 millimeters of difference. So that's 256 microns. 256 microns. 256 025 256? No, 260. 260 millimeters per pixel. So this is our scale that we'll be using. And now we can measure the points. So from here, yeah, we can measure it from here. Let's say to here. We'll try to make it as horizontal as possible. Yeah, let's make it. Let's say here. 1303. 1303 times the scale factor. That's 338 millimeters. (338) 33 centimeters. So this is the size of a penumbra here. And yeah, as you can see, the umbra can be bigger than the object casting the shadow. Penumbra can be bigger. And if the if we go, if the distance will be larger or smaller, these numbers can change, of course, they will change. And Umbra actually can be smaller than the object casting shadow. It can go to 0, actually. If you're far away, that from the wall point of view, from any point on the wall, the angular size of the, let's say, finger is smaller than the angular size of the light source, then the finger cannot occlude fully the light. There will be always some part of the light visible. Not maybe not all of it, never all of it, but as this angular dimension, angular size of the finger is smaller and smaller, you will see more and more of the light. Yes. And at the same time, Penumbra might be bigger or smaller. It would be, yeah, it might be, you might be in a situation where there's no Umbra ever, if the distances are sufficient, and all you will see is Penumbra only. And yeah, it's a little bit harder to reproduce in how you call it, a room, because the light source must be bigger. But I can maybe find a light bulb or something like that to show it. Other option is to have a bigger room, and well, in this case the bigger room will probably not help, because the problem with this demonstration is that the finger and the light source are of pretty similar sizes, right? About 10 millimeters. The light source is a little bit bigger here, but a bit more realistic demonstration will be with maybe slightly bigger light source, maybe 10 centimeters, 100 millimeters. That should be easy to do. Just a light bulb in with some diffused globe or a disc to make this source a bit bigger. The results will be exactly the same. The geometry is the same. It's just showing the other scenario of no Umbra at all, just Penumbra, will be easier to do. Anyway, I just wanted to show you that about the Penumbra and Umbra, and a little bit of processing in a program that you can do to analyze it and do measurements and pixels and plotting and important parts of the scaling using linear colors and so on. Okay, bye bye.